Okay. Tonight I'm going to show you a kind of geeky practical application of virtual worlds. It's a software debugging tool called VRmalloc. Text kind of tools to do the same sort of things are available, but I'm going to show how using a form of virtual reality can convey more information about what the program is doing and convey it better. If you add a third dimension, then you increase the information density by an order of magnitude or more. If you transform this to an animated virtual world that you can explore, you can increase this information density yet again. Now, there's a reason for this. It's because our brains have evolved specialized circuitry for dealing with 3D, for recognizing patterns, breaks in patterns, motion and depth. We have to be taught to absorb information in the form of text, and it's a lot of work. When you're reading, you're getting a few hundred bits per second. When you watch TV, it's millions of bits per second of some kind or other. So here's the geeky part. Programs usually need to borrow memory from the operating system, play with it, and give it back later. If you're doing a lot of this, it's really easy to screw up. And these can be some of the tough problems to catch because the consequences can follow the causes by seconds or minutes. Now, a second is forever in machine terms, and the trail can get pretty cold at 2 billion instructions per second. The name of the game in debugging programs is to learn as much as you can, as fast as you can about what your program is doing. Unfortunately, software tools to do this have lagged far behind the hardware tools. The hardware tools are primarily visual, oscilloscopes, logic analyzers. Software tools are still using text. VRmalloc is a software debugging tool that shows you how your program is using dynamically allocated memory. It does this by looking into it, figuring out some of its structure, figuring out where it's doing these memory operations, and then here's the interesting part, it automatically generates a symbolic world to represent this stuff in a way that's more accessible, shall we say. So I'm going to start this thing out. Now, it's generated a symbolic world to represent the program that we're going to be watching. Let's see, what are we looking at here? This is awkward. These book-looking things represent files, places where we keep the program code in visible form. And these are functions in that file. Functions are chunks of code that have some specific job to do. And these objects represent places in that function's code where some memory operation is done. Allocating memory, freeing memory, changing its size, things like that. The type of operation, different operations, different appearances. Now I'm going to start up the program that we're going to be watching here, and it will begin by allocating 1,000 pieces of memory. Zip. Now, can you see where in the program this memory was allocated from? Can you see which pieces of memory are the biggest? Of course you can. It's obvious. I don't have to explain these things. Now I'm going to release this program to go on about its business, calling functions in various files and doing lots of memory stuff. Now I know who the programmers are in the crowd. It's hard to say exactly what unless you have a particular case in hand, but you can learn a lot just by the way things are behaving here, just by the way your program is dealing with memory, allocating a bunch of chunks at once here, getting rid of a bunch, doing a bunch of random ones, things like that, changing the size of them. Now, let's see. Sure. So, watching this thing up here, watching the parts of the program up here instead of the memory, which I should have been watching, you can see where the program is using, where the program is spending most of its time and when. You can get a feel for how execution is moving around in the program, what places are busiest, the hot spots doing a lot of memory operations, what places are holding most memory. Normally, to find this stuff out, we would usually have to wade through hundreds or thousands of lines of program listings saying, and stuff like, now I went here, now I went there, now I did this thing, now I allocated this memory, blah, blah. Very tedious, no fun. If we wanted to find out more about something we saw there, we would have to type in some arcane commands, maybe a lot of them. Or maybe we'd have to type some more code into our program and rebuild it and rerun it and look at all that listings again. This is a typical software debugging cycle. We may have to do this a bunch of times just to find one bug. In VRmalloc, if you want to know more about a thing, you just fly over and have a look. Here's a busy place. We can see that this is a place where memory gets allocated. We can see a lot of statistics about it. We can see exactly where to go in the program to look for the code where this happens. It's line 45, function Phoebe, and file janus.c. Looking further down, we can see that of all the ways this could have gone wrong, exactly 0 of them have happened so far. We can look up a level at the function level and see a summary of all that stuff over all the places in that function that memory operations have taken place. Now it's time for the program to clean house and give back all the memory that it has borrowed. all the memory that it has borrowed. Looks like it lost track of a few pieces. What can we find out about this? Are they all the same size? No. Were they all made at the same time in a group? No. Were they all made from the same place in the program? Bingo. Let's go interrogate the guilty party. Now we know where to go to look for the start of the trail of finding this bug. It will be line 471, function down, and file titan.c. These are all moons of Saturn, by the way. Now, this is a class of bug called a memory leak. They're notorious. When they crop up, they can take a long time to find, hours, even days. No kidding, I've spent days chasing some of these. And the first thing that you need to find out when you're doing this is which pieces of memory actually went missing, because usually you just know, oh, the totals don't add up, and where they came from in the program. Like I said, this can take hours or days just to find out that much. This way is much quicker. Now, one of the big challenges in making this tool was that bit about automatically generating a symbolic world to represent something that isn't at all visual. Not only that, but to do it in at such a high level of abstraction that most of the tool's code has no idea what it's dealing with, whether it's memory allocation or nuclear reactor operation or air traffic control or network monitoring. All these are things that could benefit greatly from using VR as a user interface. Also, I have this plan that I'm going to make. This is going to be, the first of a series of tools that reuse much of the same code and take a similar approach to representing complex structures and activities. I might as well say it now. This is not full-on real virtual reality. Did I say that? You don't have to use gloves or goggles to use this tool. That's because the objective was to make a tool that software engineers could use in the workplace as it is today. I think this is going to change, though, as the nature of software changes and as the way that we build it continues to evolve. In the future, we may be snapping pieces of it together like Lego blocks. I'd like that a lot because instead of typing in text, well, you probably already gathered that I hate typing. The evolution of high-performance graphics, hardware, and software has been largely driven by the gaming world. If there's one thing that I want you to remember about this, or take away from this, it's that virtual reality is not just games and entertainment. It also, more and more, will include practical applications like this. Thus endeth the tale.
Thank you.